Hello students, so today we will discuss about uh, electrons in nanostructures. Now, when an electron is confined in nanostructures, that means uh, when the you know that when electron flows through a material, it has got something called a mean free path. That means the distance traveled by the electron between two collisions. So there is a collision here and there is a collision here. So this happens to be the mean free path. Now what happens is nanostructure is if we are making the structure even smaller than the mean free path, then automatically the electrons will not suffer any collision. And this mean free path is the reason that we have electronic resistance, resistance to the free flow of electrons. So if we are having a dimension which is less than the mean free path, so naturally this resistance will not occur, and Ohm's law V is equal to IR. This Ohm's law will not be applicable here. Now, now another property that electrons may have in nanostructure is if the structure is so small that if we add an electron, suppose there is already a series of electrons, a group of electrons in a certain place, we are adding one more electron to these group of electrons, that it causes an energy shift. And this energy shift is quite significant compared to what you usually have Boltzmann's constant into T. And this process of getting an extra energy shift or a significant amount of energy shift is called Coulomb blockade. Now, if you look into the free electron model, by free electron, what we mean is that the conventional electrons are non-interacting. And so what we'll get is the following distribution of the occupation index. You know that electrons follow Fermi-Dirac statistics, and the occupation index is given in the following way. So up to 1 occupation index will correspond to absolute zero temperature, that is Kt is equal to 0, and if the temperature is a little higher, then follow a shape like this. And this we have E by mu, where mu is the chemical potential, and this corresponds to Kt is equal to 0.05 mu. Now this chemical potential mu is the chemical potential, and at absolute zero, this is what is known as the Fermi energy. Now, when electrons when are passing through these very small tiny structures, when electrons they are passing through tiny structures like nanostructures, then there is, of course, as we all know, there will be the energy eigen states will be discrete. This corresponds to discrete energy eigenstates. And I guess you know what is an eigenstate if you have a little bit of knowledge of quantum mechanics. Now, as we know that the Ohm's law is not applicable, so does that mean that electrons will not have any resistance? Actually, it's not. There is a minimum resistance that is called Lambda resistance, and it is given as Rg is equal to h by 2ne square, and it is 1 by n rl. Now n here is actually the it's called the n number of channels. That means quantum mechanically we can say that there are n types of electronic wave functions which can occupy the gap. By gap means the nano dimension through which the electrons are following. And the source and the sinks are connected by these n channels. And so this RL is called Lambda resistance. And G is h by 2e square, as you can see, and its value is 12.96 coulombs. So this is the minimum resistance that an electron in a nanostructure can have. And however, these materials which are used in quantum point contact, they do not contribute to its resistance. Now, let us take an example where there are two bulk conductors connected by a small channel. And also this channel has got a bias. That means a voltage V is applied to this channel. So let's have a shape like this. This is one. This is the second one. The first conductor, there is a second conductor, and they have a bias voltage V, and this is D. Distance is D. Now, what this bias will do? This bias it will shift the Fermi levels of one relative to the other by an amount EV. Shift the Fermi level of one relative to the other by an amount EV. So it will look something like this. So this is the formula of the first one. This is the formula of the second one. So this distance is EV. Now the reason it does is that so that the net current property to number of states in the eigenstate, so that the net current flowing through them is proportional to the number of states in this energy range. And so the net current will be given as say I, it will be equal to N E V, and N number of states is dN by dE into EV. You can write it as dN by dk into dk by dE into EV. And this value, this is the velocity, the expectation value of velocity is nothing but the group velocity. Now in the allowed k states, the interval between the allowed k states is 2 pi by d. K states by means when we are looking into the Fermi reciprocal state. So if this is the interval, so the density of states per unit length is dN by dk, and it is equal to 1 by 2 pi. So the current I, which is NEVG, and which we have written as equal to dN by dk into dk by d into EV. So this one becomes 1 by 2 pi and this is, the next will be 1 by h cross square Vg into EV into EVG into 2 into N. Now this 2 comes because of the fact that there are two spin states, two electron spin states, spin up and spin down. Now, as we previously told, n is the allowed number of allowed quantum states in the channel. So by putting all these values, we get the quantum of conductance. Per channel has G0, G2 is called H, which is just nothing but 1 by RL, inverse of the reciprocal lattice, and it is equal to 77.5 microsiemens. And this Lambda resistance or conductance is a fundamental constant associated with quantum transport. So GL or G0 or RL is the fundamental constant associated with quantum transport.